All right, welcome everyone. I am absolutely thrilled to have you all here today. We are going to embark on an incredible top-down journey following a piece of data as it travels all the way across the vast landscape of the internet. Now, as your lecturer, I'm going to make you a promise right out of the gate. We are going to use the Feynman technique today. That means we're going to completely strip away the confusing jargon, and we're going to make these foundational networking concepts intuitively obvious. So let's dive right into the beating heart of how the internet actually works, the network layer.
So here's our game plan for today. We're going to cover the basics, look at forwarding versus routing, unpack the IPv4 datagram, and then dive deep into subnets, NAT, and finally wrap up with ARP. Let's get to it.
Okay, kicking things off with part one, the big picture of the network layer. So, what's the ultimate goal here? The absolute primary job of the network layer is actually deceptively simple. It just needs to deliver transport layer segments from a sending host to a receiving host. But how does it do that safely across a chaotic internet? Well, it relies on a brilliant process called encapsulation. Imagine you've written a really important, incredibly delicate letter. That letter is your transport layer segment. You wouldn't just hand a loose piece of paper to the post office, right? No way. You'd place it inside a sturdy, standardized shipping box and clearly write an address on the outside. In networking, that shipping box is the IP datagram. The sender neatly encapsulates that delicate segment into this sturdy datagram and passes it down. When it finally reaches its destination, the receiver carefully opens the box, extracts the segment payload, and hands it right up to the application. It's just a beautiful, elegant system of packaging. Moving right along to our second topic, forwarding versus routing. This is where the intersections meet the map. Now listen up, because I see beginners mix these two terms up all the time. Please don't use forwarding and routing interchangeably. They are entirely different functions. Routing is the overarching logic. It's the grand mathematical process of planning the entire trip from the source to the destination, and it's handled by complex routing algorithms. Forwarding, on the other hand, is just a localized physical action. It's the simple act of moving a packet from a router's input link to the appropriate output link. Think about routing like this. It's exactly like pulling up Google Maps or Waze right before you leave your driveway for a road trip. You type in your destination, and the algorithm calculates the absolute best, most efficient path across the entire country. It's factoring in distance, speed limits, traffic. Basically, it determines the complete route your data packets will take before the journey even begins. But forwarding. Forwarding is what happens when you're actually behind the wheel, staring down a massive, chaotic highway interchange. Forwarding isn't about the whole cross-country trip anymore. It's about the immediate, split-second decision you have to make right now. You approach the junction, look at the overhead sign, match it to your exit number, and steer your car onto the correct off-ramp. That is exactly what an individual router does. A packet arrives, the router quickly checks a table and forwards it out the correct output link. So remember, routing is the map, forwarding is taking the exit. All right, part three. Let's pop the hood and look at the actual vehicle making this trip, the IPv4 datagram. I know, this looks intense. It kind of looks like the dashboard of an airplane. But trust me, every single 32-bit row here serves a vital purpose. As these datagrams zip through those highway interchanges we just talked about, routers are constantly examining these specific header fields to figure out exactly where the datagram is going and how they need to handle it. Let's strip away the noise and just focus on the absolute essentials. Remember our shipping box analogy? Well, the source and destination addresses, which are 32 bits each, by the way, are quite literally the from and to labels written on the outside of our box. They tell us exactly who sent the packet and who is supposed to receive it. The payload data, that's our delicate letter tucked safely inside, usually a TCP or UDP segment. But I really want to draw your attention to the header checksum. This is a crucial 16-bit field used purely for error control. So how exactly does a router know if our digital box got crushed or damaged in transit? It uses that header checksum like a mathematical tamper seal. It's actually a pretty elegant logic. First, the router looks at the entire header and treats it as a sequence of 16-bit integers. Next, it adds all those integers together using ones complement arithmetic. Finally, it takes the ones complement of that final result. If the calculated checksum matches the checksum written on the packet, boom, the tamper seal is unbroken. But if even a single zero flipped to a 1 during transmission, the map simply won't add up. The router immediately knows the packet is corrupted and it just throws it away. It's a remarkably fast, highly effective quality control check. That brings us to part 4. IP subnets, or as I like to call them, our local neighborhoods. The textbook definition of a subnet is a group of device interfaces that can physically reach each other without passing through an intervening router. But let's apply our Feynman technique here to make this real. Think of a router as the central corporate mailroom in a massive skyscraper. If you need to send a letter to a different branch in another city, yeah, you have to send it down to the mailroom. But a subnet? A subnet is like an open-plan office floor. If you want to talk to your coworker sitting 2 desks away, you don't write a formal letter and send it to the mailroom. You just stand up and talk to them directly across the room. A subnet is simply a local neighborhood of devices that can communicate directly with one another without ever needing a router to intervene. Just as super quick heads up on terminology so you don't get tripped up. Historically, folks used the word subnetwork, meaning a smaller, sliced-up piece of a much larger IP network. But honestly, in modern usage today, professionals use the terms subnet and IP network practically synonymously. So if you hear someone say subnet today, they're just referring to that isolated local network neighborhood we just talked about. Next up, part 5. We're looking at network address translation, or NAT, basically the border guard of our network. Here's the harsh reality. We literally ran out of public IPv4 addresses years ago. It's a huge problem, right? Well, NAT is our savior here. Think of NAT as a super efficient corporate receptionist. Your personal computer inside the network has a private IP address, let's say 10.0.0.1. That's like your private desk extension. The outside internet cannot dial your desk extension directly. So when your computer sends a request out to a website, the NAT router, our receptionist, intercepts it. The router rips off your private return address, slaps on the company's single public IP address, and writes down exactly what it just did in a ledger, which we call a translation table. Later, when the website replies to the public address, the receptionist checks the ledger, sees the replies actually for you, and quietly forwards it to your private desk extension. It's brilliant. It seamlessly allows dozens of private devices to share one single public face. And finally, part 6, ARP, bridging the gap from IP to MAC. Okay, so we know the IP address we're trying to hit on our local subnets, but here's the catch. IP addresses are purely logical. They're just software concepts. Network cards, they don't speak IP. They speak MAC addresses, which are physical, burned-in hardware addresses. So, how do we hand a packet to a specific piece of silicon? We use the Address Resolution Protocol, or ARP. ARP dynamically links those logical Layer 3 IP addresses to the physical Layer 2 MAC addresses. Imagine you know a person's name, that's their IP address. But to deliver a physical package, you need their exact desk number in the building, that's their MAC address. ARP is literally the protocol that lets you look up the name in the building directory to find the desk number. And here is what that directory actually looks like inside your machine. This is an ARP table. You can clearly see the mapping, an IP address perfectly paired with its corresponding physical MAC address. But check out that third column, TTL, or time to live. This is a game changer. Networks are dynamic, right? People unplug laptops, they move around. The TTL ensures that the network forgets these mappings, usually after about 20 minutes. This forces the device to constantly relearn the directory, ensuring that this crucial lookup table stays perfectly up to date and never accidentally routes your data to a phantom, disconnected laptop. So how does this table actually get built? It's not magic. The devices self-learn it through a little mini conversation. Let's say host A desperately needs to send a file to host B. Host A checks its internal directory. But oh no, host B's MAC address is missing. So what does it do? Host A essentially stands up in the middle of the open plan office, our subnet, and shouts at the top of its digital lungs via a broadcast to everyone, hey, who has this specific IP address? Every single machine hears it, but only host B replies. It says, yep, that's my IP, and here is my physical MAC address. Host A gets the reply, eagerly writes it down in its local ARP table, and finally the physical data frame can be delivered. All right, so we've mapped the route, translated the addresses, resolved the hardware, and dropped the packet exactly onto the physical receiving network card. Boom. But I want to leave you with something to chew on. When that datagram is finally sitting there in the hardware, how does the receiving computer know if that data is meant for your open Google Chrome browser, your background Spotify app, or your email client? The network layer got us to the correct building, sure, but how do we find the right application room? Well, that requires stepping up to the transport layer and unlocking TCP and UDP ports, which is exactly where our journey will pick up next time. Until then, keep questioning how everything connects.